Okay. Assalamualaikum warahmatullahi ta'ala wabarakatuh, and a very good morning. First of all, let me introduce myself. My name is Najwa Ahmad Faudzi. I am from University Technology Mara, UiTM Cawangan Pulau Pinang from Malaysia. So today I would like to present my paper entitled Flexible Hybrid Graphene-based NFC Tech Antenna for Temperature Monitoring Application. So here are the list of my co-authors. So this is the contents of my presentation today. I will start with a brief introduction on NFC and the problems that has been highlighted in my paper, and the objective of my paper, materials and methods, the results and discussion, and last but not least is the conclusion. So what is actually NFC? NFC is a short form for near field communication. It is a technology that enables non-contact point-to-point data transmission between two devices over a short distance to exchange the data. So NFC is developed based on RFID, radio frequency identification, which operates at high frequency of 13.56 MHz. So the performance of NFC communication system depends on the NFC tag and also the reader, where the antenna is one of the dominant variables evaluating their performance. So the difference between NFC and UHF RFID is that we can use our mobile phone to detect the type instead of using any specific reader like UHF RFID. So the working principle of NFC is based on the inductive coupling. So the NFC reader will covers the energy to power up the chip and other external electronics components. So by placing the NFC enabled device, for example, a smartphone or smart tablet or NFC reader close to the NFC tag antenna, the energy will be harvested and able to power up the chip together with other external electronics components, including microcontrollers and also sensors. So the tag antenna is composed of conductive materials, substrate, and also NFC chip. The design of the NFC tag antenna needs to be in loop shape in order to inductively couple with the NFC reader, hence can power up the chip. So this is the working principle of NFC system. The figures that can be seen, the inductive coupling between the reader and also the tag. So the problem is that here, regarding the conductive material of the tag antenna. So normally the conductive material or the conducting elements that has been used is based on the metallic material such as copper, silver, and also aluminium. While these materials exhibit excellent electrical conductivity and mechanical properties, but they have some limitations, such as for copper and aluminium, they are easily being oxidized at ambient temperatures and also can be cracked upon bending. This can be seen here. It can be easily cracked upon a few times of bending. Other metal material based like silver, for example, it has high conductivity and it is not easily oxidized to the it is not being easily oxidized like the copper, but the problem is that the cost is way too high for silver material, making it less suitable to be used for low cost application. So therefore, carbon-based material have emerged as a possible alternative to metal-based conductive materials for the antenna conductive elements due to their low cost, oxidation resistance, and also mechanically flexible. So the carbon-based is, for example, graphene, hybrid carbon graphene, carbon particles, and so on. But the conductivity for this carbon-based conductive materials, specifically graphene, it is mostly 2 to 3 orders lower than that of the metal-based conductive material. So it is normally in the range of 10 to power of 5, 4 to 10 to power of 5. As compared to the metal-based, it is normally in 10 to power of 7 Siemens per meter. So lower conductivity as compared to the metal-based material will increase the antenna resistance and reduce the efficiency of the antenna. There are a few methods that has been applied to increase the conductivity of the graphene-based material. For example, by using a binders to prepare the graphene ink. However, the binders is incompatible with high sensitive substrate like high heat sensitive substrate like papers, PET, and textile, which require high temperature thermal annealing up to 300 degrees Celsius. Other methods, for example, stacking and rolling compression, has also been used to increase the conductivity, and it is suitable for the heat-sensitive substrate. But the challenge is that to achieve a uniform compression and also stacking. And one of the most promising method is by incorporating the metallic nanoparticles with the graphene. Here, for example, mixing the graphene with the metallic nanoparticles, but the careful material selection and processing techniques must be considered to avoid external resistance. Therefore, in this study, it is to propose a high conductivity of hybrid graphene-based material, which is composed of reduced graphene oxide and silver nanoparticle to be used as a conductive element for an NFC tech antenna. To date, there is no other researchers has been used this hybrid graphene-based material for the use of the NFC tech application. So along this research also, the analysis of the performance of the NFC tech antenna in terms of the electrical properties, robustness, and integration with the temperature monitoring circuit has been conducted. So let's go to the materials and also the methods parts and the methods parts. So we start with the synthesis of the hybrid graphene-based conductive materials. So the synthesis has been conducted through chemical reduction method. So the reduced graphene oxides is produced when further reductive exfoliation treatment is applied to the graphene oxide. So a solution of 50% reduced graphene oxide and 50% of silver nitrate, along with a reducing and encapsulating agent, was prepared and then incubated to facilitate the formation of silver nanoparticles and reduced graphene oxide. So this is the image of TEM and also SEM image for silver nanoparticle for the hybrid graphene-based conductive material, and it can be seen here. The silver nanoparticle exhibit a particle size distribution ranging from 10 to 25 nanometers. And from this SEM image can be seen that there is a good attachment between graphene and also silver particle, which contributes to the high conductivity of the material. The conductivity of the material also has been measured by using 4-point probe system here, where the average or the mean conductivity that has been achieved is 3.95 times 10 to the power of 6 Siemens per meter. So there are three designs has been proposed here by using the hybrid graphene-based material as the conductive material. Where the design here has a variations in terms of the size, the width, the gap, and the number of turns. And the simulation has been conducted by using CST simulation software. Okay, so the discrete port here, NFC chip, text from Texas Instrument has been integrated with the internal capacitance of 35 picofarad. So from the simulation, among the three designs here, design A, B, and C, both of the design A and design B has achieved similar Q factor value, which is 1.2, which is higher as compared to the design C. This is because of the wider coil width here for design A and design B as compared to the design C, which reduced the antenna resistance, where the higher the width of the coil here, the lower will be the resistance of the antenna. And however, when we compare design A and design B, it can be seen here that design A has 20% much smaller size as compared to the design B, making it more suitable for placement on various items and surface without overly being bulky. Therefore, design A is chosen as the most optimum design and has been used for printing and further analysis. So this is the fabrication process of design A by using the proposed hybrid graphene-based material and using the inkjet printing method. So this is the prototype of the design A antenna. So now we go through the results and also the discussion parts. Okay, so this is the three samples of printed design A antenna by using hybrid graphene-based conductive material. So the first measurement that has been conducted is to measure the inductance and also the resistance of the antenna by using vector analyzer here. And the result has been compared with the simulated value. So from this measurement, from the result here, we can be seen that the measured value in average agrees well with the simulated value, and these findings demonstrate that the graphene-based conductive material is well printed and compatible with the flexible PET substrate. Okay, we can see here the inductance of the tech antenna is 0.9, and from the simulation is 0.75, which is almost similar to each other. Okay, so the measurement of the tech reading range also has been conducted, where the measurement of that reading range has been conducted using this NFC enabled smartphone. For example, here I'm using a Xiaomi 11T, and the distance between the reader and the tag has been measured by using a penny caliper. So the measured and also simulated result has been compared. So this is from the simulation, where it can be seen that the maximum tag reading range achieved is 3.2 centimeter, where the maximum distance was observed at 1.5 ampere per meter of the magnetic field strength, which is the minimum strength required to power up the tag antenna. So this is the results that has been achieved from the measurement, where we can see that the maximum tag reading range is around approximately 3 centimeter with the tuning capacitance value of 75 picofarad. So the results for the simulation and measurement agrees well with each other, and the result falls within the typical detection range for a smartphone, which is within between 1 to 5 centimeter. So the effects of bending also has been observed and analyzed. Okay, the tag antenna was attached to different type of cylinder foam, and the shift of the antenna resonant frequency has been analyzed and observed through using the VNA. And we can see from the result here, it can be seen that the bending does not give a large impact to the tag antenna, where we can see the resonant frequency is almost constant with the various bending angle. Okay, and only when the cylinder foam 1.5 centimeter, which is equal to 190 degree of bending, the resonant frequency is shifted slightly to higher frequency, approximately 1 megahertz, but it is still within the acceptable range. Okay, but as we can see from the reading range here, as the bending angle is increased, we can see that the tag reading range is reduced from 2.4 centimeter to 1.3 centimeter when the bending angle is increased from approximately 60 to 190 degree. So this is because the antenna, when the bending angle is increased, the antenna's accessible surface area is reduced when the bending angle is increased, which consequently reduce the induced magnetic field in the tag antenna and reduce the tag reading range. Okay, we can see also from these results here, the distribution of the magnetic field from the simulation here. As the bending angle is increased, the distribution of the magnetic field also will be decreased. So that is the reason why the tag reading range is reduced with the increase of the bending angle. Okay, the sensitivity of the tag also has been analyzed while the tag was attached to different surface material. For example, plastic, carton box, woods, and also metal. And from this S11 result, we can see that the tag is not much affected when it is attached to plastic, carton box, or wood material. But when it is attached on a metal surface, we can see that the performance has been significantly reduced. This is due to the existence of the eddy currents on the metal surface, where the current on the opposite direction has been generated, which will cancel out the magnetic field induced by the reader. So last but not least is the integration of the tag with the temperature sensor. Both the tag, antenna, and also the circuit here has been printed by using the graphene-based conductive materials. So the sensor that has been used here is NTC thermistor from Sunlot. So this is the schematic diagram. And this is the equation that has been used where the temperature is related to the resistance of this NTC thermistor. So the temperature has been wirelessly monitored by using the smartphone and also the apps, the NFC temperature monitoring apps here. You can see the apps here. It is an enhanced apps from the previously developed apps from the Texas Instrument. So enhancements has been done to make it suitable to be used for the graphene-based tag antenna, where the regression of the value for the apps temperature and the real temperature has been measured. And also from this two-step linear regression that has been performed, two equation has been achieved, where both of these two equation here, both of these equations has been incorporated into the apps coding in Android Studio, and the final result can be seen here from this final correlation. We can see that the real temperature and the apps temperature has achieved a good relation, where the temperature difference is within plus minus 2 degrees Celsius. So it is suitable to be used as the temperature monitoring application. So the proposed conductive material has been that has been proposed has been compared with the previous study. So it exhibits the highest conductivity value as compared to other materials in the previous work. And despite of its lower printed thickness, it still achieved performance comparable to other graphene-based NFC type, particularly in terms of the reading range and application. And in terms of the reading range, although it is lower than the this reference 8, it still meet the required reading range when detected by a smartphone, typically between 1 to 5 centimeter. And regarding the size, most tags from previous works are bulkier than the proposed tag, which may limit the attachment to certain items. Okay, and in terms of the integration with the circuit, the proposed tag is the one that is flexible as compared to other previous work, which has been used PCB fabrication, which is not flexible. So in conclusion, the hybrid graphene-based material has been successfully validated for NFC tag application, and the maximum reading range achieved is 3 centimeter. It is also capable to withstand bending at various angle, with maximum reading range up to 1.3 centimeter at 190 degree of bending. So consistent performance also has been observed when the tag is attached on various materials, including plastic, cotton, and wood, except for metallic surface due to the existence of the eddy current. So integration of the flexible circuit also showing temperature readings with minimal difference within plus minus 2 degree between the actual and also the apps temperature. So in the future, the application, the real world food quality monitoring will be applied at different temperature range, cold, such as cold room and also hot temperature. And the alternative substrates such as TPU, thermoplastic polyurethane, which offers stretchability, could be explored to improve the durability and flexibility of the tag. So that's all from me. Thank you.